Hello everybody, welcome back to our lecture series on satellite communications. Today let's talk about noise. This is our missing link in our system design, looking what's going on with noise. I have to move this now. Some of you, maybe the older ones of you, can remember the good old days of analog TV. When you have an analog TV set and you do not receive any station, you can actually see something on the screen. And you see white and black dots. When you look closer, they're actually colorful dots. And this is a received signal where there is no signal. And that's what we know as noise. And I have a second example here. I started my spectrum analyzer and my oscilloscope on the desk, and you see that on the oscilloscope on the top, even though there's nothing attached to our ports, we receive a signal, and the signal is a funny sizzling line going up and down. And the same on the spectrum analyzer. Also, the spectrum analyzer is empty, nothing attached. We still see a signal, and the signal is more or less a straight line, which also goes a little bit up and down. The values cannot be seen here. However, you can clearly see the up and down on the spectrum analyzer and the wavy line here on the oscilloscope. That means even in the absence of any signal, we receive something, and that's what we know as noise. I have my own definition for noise. It slightly differs from engineer to engineer. In my definition, noise is just unwanted energy which interferes with the proper reception and reproduction of the transmitted signal. Whatever we receive and can suppress, or it's out of band, it's not really noise considered, because it doesn't interfere with the reception of my signal. Okay, let's take a look in noise, and let's characterize what noise is. Noise is most important on the receiver side. When you're a receiver, you receive your signal here, and the signal is picked up by the antenna. From the antenna it goes into the receiver, and the receiver is amplified, filtered, demodulated, and so on and so on. And then on the other side you get the signal out. And the signal out is actually what you are interested in, or what we are interested in. The amplified, demodulated signal. Well, unfortunately, not only receive noise, we not only receive a signal, we also receive noise. The stuff I just showed you on the oscilloscope. This noise is also picked up by the antenna. It also goes through the antenna into the receiver, it's amplified, demodulated, and so on, and comes out of the receiver. And even worse, inside my receiver, I create additional noise. Every receiver in the world, every transistor, every amplifier creates additional noise. And this noise also goes on top of the noise picked up, and we get noise out here at the output. And now the big problem is, or the big question is, when we receive the proper signal here and we receive the noise, can we still hear what we want to hear in the signal in the presence of the noise? And as you see, and it's obvious, important is the ratio between the two. When you have lots of signal, you can also afford lots of noise. When you have a tiny signal, which is really quiet, you also have to make sure you only receive a small amount of noise. And this ratio is known as the so-called signal-to-noise ratio. And I consider, as a communications engineer, the signal-to-noise ratio the most important number in the life of a communications engineer. Everything you build, everything you own, everything you want to sell basically boils down to having a good signal-to-noise ratio. The better the signal-to-noise ratio, the better your system usually is. So, and that said, we already talked a lot about the signal, how it's picked up by the antenna, how big is the received signal and so on. Now let's concentrate on the noise, because we have to know both. If we know only the received signal power, it's pretty useless. We, in addition, also have to know what the noise level is all about. Okay, then let's go and see what noise is and how big it is. I basically did these definitions here. The higher the signal, of course, the better the demodulation. No? Higher ratio is good. And when we look into digital systems later on, we'll see that the signal-to-noise ratio is very close related to the number of bit errors you detect. The higher the signal-to-noise ratio, the less errors you get. And that's usually a good thing. That's why when you want to have a low bit error rate, you need a high SNR. But that's something we really going to look into next time. SNR is a ratio, and engineers like to express ratios in dBs. That's why we often see our SNR given in dBs. Where does my noise come from? Well, we have to distinguish between the internal generated noise and the external noise. Internal noise is the noise that's created inside my receiver, and there's most important, by far most important, the thermal noise, which is what we're gonna concentrate our lecture today on. Then we have something that's called shot noise and flicker noise, and also we have other noise sources inside my receiver, so-called electromagnetic interference, EMI or EMC. That's when you have in the receiver one signal that interferes with the other signal. That's also considered noise. In addition to my internal sources, which we have most control of, we also have external sources picked up by the antenna. So we'll see in 10 minutes that an antenna produces noise due to the temperature of the object on the ground. Also, the atmosphere generates noise because it's also at a certain temperature. Then we have so-called industrial or man-made noise. That's noise created by other machines, by other people, by cars, and so on. You may remember when you're sitting somewhere with your radio, an FM radio, and there's a scooter driving by, and you hear this funny noise in the radio. That's man-made noise. And then also something very exotic, but it's not neglectable in our case, the so-called extraterrestrial noise, which comes from our sun, the solar noise, and also from other suns, from other stars, which is known as the cosmic noise. I'll take a quick look at these things. Let's talk for 1 minute about the noise sources which are not of interest. The first one is the so-called shot noise. That's created due to the fact that electric charges flow through a wire in packages because they are quantized. And they are discrete packages. And since they are discrete, they do not have an extreme constant flow. And the flow of electrons or charges varies a little bit due to this package nature. And we get a so-called shot noise. Similar to a shotgun, where the bullets come out not continuously, but in little packets, basically. And the amount of shot noise can be quantified by this equation. However, this shot noise is extremely small. So it's basically neglectable for what we're going to talk about. That's why I don't look into this. The second noise type we can observe is the so-called flicker noise. When charges or electrons move through barriers in a semiconductor or other structures, or between two different metals, they don't go there extremely continuously, but they also come in with up and downs, and that's a so-called flicker noise. And the flicker noise has the as a type that it changes with frequency. It goes down with 1 over f over frequency. And as you can see here in this chart here, it's a chart from an analog device operational amplifier, and you see the noise produced there. And when you look at the frequency, the level of noise goes down with frequency with 1 over f, and on a log scale it's a straight line. And then at higher frequencies the noise stays constant. They call it here the broadband noise, but this is what I call the thermal noise. So now look at the frequency where the thermal noise becomes a constant noise at this range here roughly. Let's go back to my... So we have this range here, and in this range actually we're talking about frequencies of 100 Hertz to 1 kilohertz. So compared to our microwave frequencies of gigahertz or megahertz, this is way, way lower than we're going to look at. That's why also forget about our flicker noise. We don't need it. The third type of noise observed in electronic circuits is the so-called thermal noise, and that's a noise that's important for us because it's the dominating noise in any communication system at microwave frequencies. What is thermal noise? Well, let's take a look here. Try to make here like this. When we have a resistor, I made the resistor really big, and the resistor is at a certain temperature. Then inside my resistor I have lots of charges, like electrons, and these electrons, they actually move around because of the thermal movement, the Brownian movement, and the electron hits back and forth, and every electron does this. Every electron, it hits into another electron in an atom, in a core, and so on. So all of these electrons are in motion. And due to the motion of the electrons, you will, by accident, have sometimes much more electrons down here than you maybe have up here. When you have that case, then you have a negative charge here and a positive charge here. And that means you measure a positive voltage at the terminal. So basically I measure a voltage, maybe like this. A few microseconds later, well, the electrons are not down here, the electrons are up here. Oops. So now our voltage becomes negative, no? Positive here, negative there. So my next point will be somewhere down here, and next time they are evenly distributed, so maybe the voltage is 0, and then the electrons are down again, or they go up here, they are here, next time here, here, and so on. So when you connect those lines all the time, you see that actually you observe something which looks like this. You observe a tiny voltage that goes up and down. And when we look at our oscilloscope here again, you see that effect here. The voltage is going up and down. And you see the voltage is tiny. It's already at 1 millivolt per segment per square. And that means it's like maybe a few microvolts, not more. No? So even though the observed voltage is small, it's there. No? That's what's known as thermal noise. No? Oops. Okay. So the thermal noise is the random thermal motion of the charges or electrons, and it is created inside any resistor, but also in any transistor, sorry, and diodes and so on. So it's everywhere. When we look at capacitors and inductors, we usually can ignore it because those elements have very small resistance, so it doesn't produce a lot of noise. The thermal noise is also known as Gaussian noise or white noise, and I'm going to explain this in a second why it's also known as Gaussian noise or white noise. It's the same thing. Thermal noise, Gaussian noise, or white noise. It's all the thing. When we look at the value here of our voltage, the value differs. However, when we look at the average power, then basically we square that line. Let's see. Over time we can measure some power. Power is P is voltage squared over resistance. And then we can, well, this here squared becomes something like this squared is this, and so on. So you get some power, and the power is always positive. So on average, we will be able to detect the power level that is, let's come here, that is maybe here. So that's my so-called noise power level. When we go into the physics of the resistor and the thermal movement, we can actually figure out a formula for the amount of noise power produced. So the noise power, Pn, most often noted as just N, is my voltage squared over the resistance. There's also a 4 coming in because it's double-sided, and also it's not the peak value but the average value or the RMS value. That's not of interest right now. What's interesting is actually this thing. My noise power is K times T times B. And that's a fairly simple formula, but that's an important formula for our noise, because that determines the amount of noise produced. K is the so-called Boltzmann constant. It has a value 1.38 10 to the minus 23 joules per Kelvin, and named after Stefan Boltzmann, a very famous physicist. And T, maybe let's go here. So K is my, let's forget to switch. K is my Boltzmann constant. T is my temperature. And B is my bandwidth of the signal. Or the signal of system. Let's put it as this. So you have to, when you know these three values, you know the amount of noise power produced by a resistor. Should be noted that the noise power is not only created by resistors, as I said, also by transistors, and we'll see in a second also by antennas. Now, we have one problem. The noise voltage or the noise power, the instantaneous noise power, cannot be predicted. So, it's yellow here. So, okay, now cannot be predicted. It's a stochastic signal. That means it's totally arbitrary. There's no way to figure out what my noise voltage is going to be in 2 seconds. So that's why it's called a non-deterministic or stochastic signal. Most likely you have heard about stochastic signals. They're everywhere in engineering. That's why it's not a very big surprise that it comes to you. As we cannot predict the voltage, we have a problem. Nevertheless, we can make a lot of, we have a lot of information about our signal, even though we cannot predict our voltage over time. That said means our time series of my noise is not very useful. However, more useful is the Fourier transform, the frequency spectrum of our noise, and our probability distribution function, which tells me how is the probability of our voltage value distributed. And I'm not sure what my next figure is about. Yeah, but oh, let's do this. Sorry. Now, here we can see the three different types. My time domain signal looks like this. Now remember, that's my signal from the oscilloscope. To the right, we have the signal from the spectrum analyzer. And when you look at it, and I can also go here and average a bit. And sorry, press the wrong button. Again, I press the wrong button. So when looking at our lab test again, so here you see the up and down of the time series, and here I averaged a bit. You see basically a straight line, and this straight line is my frequency domain response of my noise signal, and it's very surprising, but over in the frequency domain, my time domain, my noise signal is just a straight line. So it has all frequency components with the same weighting in it. Low frequencies are as much in the signal as high frequencies. And since they are all frequencies in the signal, all with the same amount of power, when you look at it from the light perspective, then you have something like you have low frequency light here, and something is wrong with my settings. You have low frequency light here, which is red, medium frequency would be green, and high frequency would be blue. And we can even do that here like now. So here we have reddish light, here we have greenish light, and we have bluish light. And when all the light components are in the same amount, all three together combined become white. Or all frequencies together are white. And that's why this type of noise is also known as white noise, because all frequency components are in there with the same weight. That makes it a white signal. Okay, but that's just a side note. So, as we said, time domain signal is quite useless. Frequency domain signal is really nice because we have a constant noise density, spectral density, sorry. And the third way of looking at it is the probability density function, which gives me the probability of a certain amplitude in my signal. And I'm pretty sure you have heard about that before. When you look at the time domain signal, it's more likely, it's more likely you have small signal components here, or you have zero, it's most likely, then you have big ones. You can even have signals here, but they are very unlikely. And that's expressed by this curve here. Most likely is high values that the signal is around zero, and very unlikely, but not impossible, that the signal is either at -10 or +10 volts, something like that. No? That's my probability density function. And in math and acoustics and so on, you look much more into these kind of things than you do it here. For us, most important is our friend. Let's go here. For us, it's most important, this guy here, the density function. Here's a little Python code which just plots these three diagrams, and there is a line here. Again, wrong button. Much too big. There's one line here, this one, where my random signal is generated, no? Random normal, with a certain center value and a certain sigma. And here the three plots give just plot out the signal, nothing else. No? And when you do that, you get here the time domain signal. Here you get the probability density function in bins. It's a so-called histogram. And here you get the power spectral density, my frequency domain response with found by an FFT. Here, or probability density, PSD. And it looks like this, and you see clearly the straight line the signal follows. No? The straight line is not perfect because we are not looking at an infinite long signal. However, it's there. Good. If you like, you can stop here and copy the program, or I can give it to you and you can try it yourself. Now let's take a bit closer at our signal here. As I said, the probability density function is, the power spectral density, the power spectral density here, no? Is constant. In this case, it's minus 18 dB per hertz. dB per hertz means there's so much power, or watts per hertz, that can also be expressed in watts per hertz here. No? There are so many watts per hertz in the signal per hertz bandwidth. No? And in order to find the total power in the signal, you need to know your bandwidth. No? For example, when I'm going from 0.2 to 0.3 here, hertz, then, and since it's normalized, it's very low frequency, no? This is my bandwidth, then my total power in that band is this area. No? And this area is my density here, which is this number. And the density is, well, K times D, and times my bandwidth, and I have the box. No? More general, that would be an integral. No? I just showed you in the next slide. No? So just putting it together, you can say your power n is my power density, called n naught. That's this value here, n naught. And n naught times my bandwidth. No? And n naught, remember our slide before, is nothing else but K times B T. No? So we can write it like this. No? Spectral density K times T times B is this. No? When we increase our temperature, this line walks up. No? If we decrease the temperature, this line walks down. And that's as simple as that. Now, there's a little twist to it that comes from the fact that system people, they like to also look at the negative frequencies as well. When you look at negative frequencies as well, then your signal keeps going like this here. No? And now your bandwidth in that area is not 0.1, 0.2 in positive, but also 0.1, 0.2 in negative domain. That's a system engineering or system theory standpoint. So the actual area is 2 times this. And that's why my spectral density n, this n here, n of omega, or f, is not just n naught, as I've shown you before, but it's n naught over 2. No? So a little, it's unfortunate, but there are 2 different definitions around. Either people use only positive frequencies, then my p is just k times t times n naught. Otherwise, you have to divide it by 2. No? But it's quite obvious when you see that in your application. And for us as microwave engineers, it's not a big issue because we just look at this formula here, no? And we are happy. Okay, yeah, that's what I wanted to explain here, and I have already explained. Good. Coming back to our, let's go back once more, to this guy here. We can also express the power density, the probability density function, sorry, and that's this well-known formula about Gaussian noise, Gaussian distribution, and the Gaussian distribution follows this formula here. You have most likely seen it. It's exponential times something squared, no? And that's something that's squared is my voltage here, and then it's normalized by 2 sigma square, and also here with this normalization factor square root 2 pi sigma square. That gives me exactly this bell-shaped function. No? And interesting to observe the sigma square as the variance of the signal in terms of stochastic analysis, and that's my medium noise power. My medium noise power is my RMS squared. No? Voltage RMS squared. No? That's medium noise. That's medium power. No? As you know from first semester bachelor. That means that, down here, that the sigma, because sigma square is my noise power, the sigma is nothing else but my RMS value of my voltage, the RMS value of the noise. So when you want to plot here your noise power, you just have to, and in my case here it's just 1, the RMS value. You can just do it by this connection between sigma and the average or the RMS value of the voltage. Okay, another slide on that. I repeat myself what I've shown you before. The so-called noise bandwidth is the noise per hertz, and the noise per hertz is just my k times t. So let's do a little example and you can see what happens. We have a resistor at temperature 1000 Kelvin. Find the noise power, it should be W here now, for a filter bandwidth of 36 megahertz. Well, that's straightforward. My noise power is k times t times b. We know t is 1000. This is 1.38 10 to the minus. Oh, let's make it nice here. 1.38 10 to the minus 23 joules per Kelvin. T is 1000 Kelvin, and my bandwidth is 36 10 to the 6 1 over seconds, no? Because it's hertz. So now joule is watts seconds, no? And that means we can cancel out this k here, we can cancel out the seconds here, and we end up with a value in watts. It must be, no? Power. So I have done this on the next slide, and you see that my n, I first calculated my n naught, which is just the k times t, and which is 1.38 10 to the minus 20, because times 1000. Then I do the calculation I have done on the slide before, which is my k times t times b, and I get 4.97 10 to the minus 13 watts, and that's a typical value, like a tiny value you see. And when you convert it to dB watts, it's minus 123 dB watts. When, just assuming, when I have a signal of minus 92 dB watts coming in, then I can find the SNR. And the SNR, remember, my SNR is signal over noise, and then my SNR in dB would be signal in dB watt over is minus noise in dB watt. No. And when you do that, minus 123 and minus 92, then you have signal is minus 92 minus 123, then you get 31 dB ratio. You may stop the video now and do the same calculation using absolute values. No? You can convert this here. You can convert this in absolute value in watts, then you have this in watts here and this in watts, and then you can find the absolute value and then you can find the ratio. It should also be 31 dB. When you come in with noise, it usually has all frequency components in it. Then you go into your system, and your system behaves like a bandpass, something band limiting, and then on the output you get only one band out, and that's why you have a limited amount of noise. Otherwise, you would have infinite amount of noise in the system. And the total, I repeat myself again, is my density times my frequency bandwidth, or in case of double-sided, 2 times that. No? When your bandpass is not constant, or the noise, then you have to do the integration. But that's something we are not going to do here in our lecture. We just stick with our constant term where my noise is k times t times b. Good. I skipped that one and come directly to our antenna. Now, what does it mean for a system having an antenna? When you have an antenna, it's extremely simple because the antenna picks up the noise here from its surrounding, and you have electromagnetic waves coming into the antenna. Where do the electromagnetic waves come from? Well, they come from any object the antenna is facing, for example, that tree. Inside that tree, you have electrons. No? These electrons are moving up and down. No? By this movement of the electrons up and down, remember, they create electromagnetic waves. And these electromagnetic waves are the waves that hit the antenna. No? Every object at a certain temperature does it. That's why we can define now our picked up power. The picked up power is, and just following this equation here, the noise picked up by antenna is K times the antenna noise temperature times B. TA is the so-called antenna noise temperature. And this antenna noise temperature is the same as the object that it's pointing at. In this example here, a tree. That's why we can say TA is, well, just the temperature of the body. When we look at it in terms of satellite communications, you have an antenna in space that's pointing to the ground. Then the antenna sees the ground here. And that ground temperature is the temperature of the noise picked up by the antenna. And since the ground is roughly at 15-20 degrees, you can say, well, in Kelvin, this is about 290 Kelvin. 290 Kelvin is a normal noise temperature for any object on the ground. That's what engineers agreed on. So this antenna behaves exactly as a resistor being at 290 Kelvin. Produces the same amount of voltage fluctuation than a resistor at 290 Kelvin. That's why it's easy to model this antenna. When the antenna is pointing the sky, then let's say this is my Earth, I have my antenna here, it's pointing in the sky, then it gets noise from other sources, and those sources are, well, various. Most important is noise coming from the sun, because the sun is so hot, you receive lots of noise from it. You receive noise from the moon, and you receive noise from the surface of the Earth, because the antenna still sees some of my ground here, and there are trees and houses and so on, so it picks up also noise from the ground, no? And also noise from the sun. However, the sun is fairly, the sun is fairly small, no? When you, the angle it gets from the sun is extremely small compared to the angle from other directions, no? Let's say from this here, no? That's why the noise picked up by the sun is neglectable unless you're just pointing a high gain antenna directly in the sun. You have to be careful because then you get lots of noise. When you have rain and so on, here, rain is also at a certain temperature, that also produces a lot of noise. So you have to add this to, well, not add, but basically you get noise much higher than oil. But when the antenna is pointing in the direction where there's nothing, you still get noise, and that's extremely interesting. That's something that was first observed in the 1950s. Some people built a gigantic horn antenna, as you see on the left side of the figure, the Horndale horn antenna. And they pointed this antenna at areas where there's no star and nothing, absolutely nothing, total black. And when they when they looked at it, they actually figured out that they received the signals, very weak, but about 5 kelvins when you convert it into a temperature. So when you point in a direction in the sky where there's nothing, you receive a signal of 5 Kelvin. That means there's something at the back of the universe, the so-called cosmic background radiation, that creates 5 Kelvin temperature. And it also depends on the direction. When you're here in the direction of the Milky Way, then you get, of course, much more noise because there are much more stars than when you go into other directions. However, even in direction where there's nothing, you still have a few kelvins of noise. This is one of the major building blocks of the Big Bang theory, because that means that you can actually determine the distance. It's about 18.9 billion light years away, that you receive 5 Kelvin signals from 18.9 billion years away, light years away, but there still is a signal. That means 18.9 billion years ago, this signal was generated, and so there's something, no? And then this, when you go 15 steps further, ends up in something like which is now known as the Big Bang theory. No? That's one of the major proofs or ideas of the Big Bang theory. This picture here. No? Antenna noise depends on my frequency and on the direction I'm pointing the antenna. No? When this is my ground, and I point my antenna here directly upwards, I receive little or no noise from the ground here. No? That's here the ground noise, not coming in like this. No? When I point my antenna parallel to the ground, of course, I pick up some of the ground noise. No? That's why this noise I pick up with my antenna depends from the angle with respect to the zenith direction. No? So when this is my zenith direction, then this is my angle theta. No? And this is plotted here. And it strongly depends on the temperature, it strongly depends on the frequency, as the atmosphere of the Earth also absorbs and creates noise. You have an area between 1 to 10 gigahertz where your noise level is fairly low, and outside these regions your noise level is getting higher. That's why you usually try to restrict satellite communication to the frequency range 1 to 10 gigahertz. Looking at this figure here, when I'm pointing towards zenith direction, that's 0 degrees, then you can get noise figures here at 10 gigahertz and so on, here down this line, of only 5, 6, 7 Kelvin. No? when you're pointing your antenna on the horizon, then you get noise figures which lie somewhere here, which are around 100 kelvins. No? It also depends on the frequency, as you see. This chart is important later on when you do your project and when you want to figure out what your actual noise level is of your receiving antenna on the ground. Last example, and then we do a little break. We have a satellite link at 5 gigahertz, and the ground station antenna is at an elevation angle of 30 degrees. Find the antenna temperature and total received noise for a 10 megahertz bandwidth. Well, we look at 5 gigahertz here. 1, 2, let's go this here. 1, 2, 3, 4, 5 is here. And we have an elevation angle of 30 degrees. This is from 10 at 60 degrees. That makes it this point, and then we get here, see, I get like 8 Kelvin. I think I used 6 Kelvin in my calculation, but anyway, so I get a few kelvins, and as I said, I use 6 kelvins here for some reason. In my calculation should be more like 8 or 9, no? Anyways. And now we can calculate the antenna noise temperature on the ground and on the satellite. No? On the ground, we have our K value times my ground temperature, which is 6 Kelvin, times my bandwidth, which is 10 megahertz. That gives me 0.828 femtowatts. And converting this gives me minus 120.8 dBm. In the satellite, we are in the sky, and we are pointing, well, take a look again here, ground station antenna, satellite antenna. My satellite antenna is facing the ground and has thereby 290 Kelvin. And I get K and B, and I get, when I calculate all of that, 40 femtowatts. So you see about a factor of 50 times bigger, and that also reflects in the dBm value. Now you get 17 dB difference in your dBms. No? Maybe try to do the calculation yourself as a little exercise. No? Well, when I receive a signal of 20 femtowatts, what my SNR? Well, that's easy now. My SNR is my signal power divided by my noise power. Noise power was 0.828 femtowatts. So signal power was 20 femtowatts. So the ratio is 24.155. And this converted into an SNR becomes 13.83 dB. So, okay. Well, try to do everything in dBms and then substrate. Yeah. See what happens. You should get the same result. Okay, now we learned a lot about noise already. Let's have a little break and relax and do some exercises, and then we come back in the second part of the noise lecture, which is about the receiver noise inside the receiver and cascaded noise, and how do we get the total signal to noise ratio when you put everything together. Okay, thanks for listening.